A hearty welcome, children, for all the beloved 10th standard students for session number 8, chapter number 2, triangles. Dear children, how are you children? Hope you are all doing very well. Please maintain the social distance, drink as far as possible hot water only, children, and avoid taking food outside as far as possible, children. You know that health and education are very important to us. Okay, fine. Take care, children, take care. Dear children, this is the concluding session for the chapter number 2, triangles. Oh, nice. Yes. In our previous session, that is the 7th session, we have understood, okay, the theorem on areas of similar triangles as well as the worked example number 9 and the general enunciation of Pythagoras theorem with the help of an activity. Can you recall them, children? Okay. What was the homework? The homework was exercise 2.4, which has 9 problems. Okay. Hope that you have done the homework with all dedications and sincerity, and you have to show it to your teacher, children, so that you will get some more informations and tips from your teachers. Okay. In this session, let us perform one more activity, children, to demonstrate Pythagoras theorem practically, children. Okay, look at this model. Here is a right angle triangle in deep blue color. Okay, this angle is 90 degrees. Therefore, this is our hypotenuse, correct? So, here is a square built on the hypotenuse. So, all these 3 sides are equal to the hypotenuse and these 4 angles are equal to 90 degrees. In the same way, here is another square constructed on this side of the right angle triangle. So, all the 4 sides are equal and all the 4 angles are equal to 90. Again, here is a small square built up on this small side of the right angle triangle. Okay. According to Pythagoras theorem, the area of this square on the hypotenuse is equal to the sum of this square and this square on the other 2 sides. Children, this can be beautifully demonstrated with the help of 4 quadrilaterals like this. So, they are identical quadrilaterals. You should prepare the 4 quadrilaterals like this and one more square like this. With the help of this, we can easily demonstrate Pythagoras theorem. Here we go. So, let us take one quadrilateral and place it like this. Okay. So, take the second piece, second quadrilateral, children, and try to accommodate like this. So, 2 quadrilaterals have been placed. Now, take the third piece, children. So, this you have got to keep it like this. Okay, this is the third quadrilateral and the fourth one will fit exactly into this. In other words, the square here, the area of the square is made up of 4 quadrilaterals which are identical to each other. Okay. What about this? This area can be easily fitted with the help of this square. Okay. Now, what is that we need to show? That area of this square is equal to sum of the areas of these 2. So, if this is really true, these 4 quadrilaterals and this square should be easily accommodated into this. Shall we try that, children? So, let us take one by one. So, one quadrilateral I have taken it out and we will place it like this. Okay. The second one we will take it out and accommodate like this. Okay. So, here is the third one and we shall try to place it like this. Okay. And this last one can be taken out and can be placed like this. Okay. See, so beautifully the 4 quadrilaterals are arranged now. It's so nice to see here now. So, this square, the area of this square is definitely equal to this. So, area of this square is exactly equal to this. Wow! So from this we can understand that the square on the hypotenuse is equal to sum of the squares on the other two sides. In fact, this kind of a dissection is called perigal dissection, children. P-R-I-G-A-L. Dissection means to divide it into many parts. So this is called perigal dissection. He was a British stockbroker and an amateur mathematician. If you want any more details, you go to YouTube and just type perigal dissection. You will get lots and lots of information on this. Now, having seen it practically, let us learn the theoretical proof for Pythagoras theorem, children. Okay, its converse as well as some worked examples also we will try to see this. Okay, now. So, Pythagoras theorem. Okay, among all the theorems that we are going to study in the high school geometry, children, Pythagoras theorem is the most popular theorem in the world, children, and today this is called theorem number 2.8 in our textbook. So, shall we prove this, children? Before that, we will state the Pythagoras theorem also. So, can we state the Pythagoras theorem looking at the 4 right angle triangles and the 4 squares or the 4 corners, children? Yes, come on, start. In a triangle. Is it true in all triangles, children? No. So, it is true only in which triangle? It is true only in the case of a right angle triangle. So, you must say that in a right angle triangle, what is that we have to do? We have to take the square. On which side, children? On the which side we have to take? We have to do it on the hypotenuse. So, the area of the square on the hypotenuse is exactly equal to the sum of the squares on the other two sides. Children, normally in the public examination, you will be asked to state one particular theorem from our textbook. This is how we have got to state the theorem. So, let me state once again, in a right angle triangle, the square on the hypotenuse is equal to sum of the squares on the other two sides. This is called general enunciation for Pythagoras theorem. So, the first task is we have to draw the necessary figure exactly. Here is a right angle triangle ABC, in which angle ABC is equal to 90. Therefore, AC is our hypotenuse. So, what is the next step? So, we have got to write data. Means given. What is given in the theorem? In right angle triangle ABC, while writing the triangle, you better write right angle triangle only in data also. In right angle triangle ABC, angle ABC is 90 degree. Anything else is given, children? No, that's all. This is a right angle triangle. We have to show that AB square plus BC square is equal to CA square. What do you mean by AB square, children? AB into AB. Why AB into AB? You know that area of a square is length into length. Therefore, AB into AB is equal to AB square, which means the area of the square on AB plus BC into BC is BC square is exactly equal to CA square, children. Children, you know that this theorem has attracted the attention of many mathematicians in the world, children. So, as on today, we have got nearly 300 different varieties of proof, children, but our textbook demands the proof which is based on the similar triangles which we have understood in the previous sections. So, in order to prove this theorem using similar triangle concept, I think we will have to recall theorem number 2.7. Yes, come on, tell me what is the construction. Can you suggest the construction, children? Yes, we have to draw the perpendicular BD to our hypotenuse. So, mark the angle as 90 at the point D. So, therefore, the construction is we have to draw BD in dotted lines only to show that it is the construction and not given in the theorem. I think you can see now there are 3 pairs of similar triangles are there. All the 3 of them are right angle triangles. So, let us take one by one and try to prove Pythagoras theorem. Okay, here is a right angle triangle ABC. Okay, so let us suppose that angle BAD is equal to x degree, children. okay, in order to make you understand. If angle BAD is x degree, what about angle ABD, children? Yes, it has to be 90 minus x. When angle ABD is 90 minus x, what about angle DBC? It has to be x, okay, because 90 minus x plus x is equal to 90. Therefore, in right triangle BDC, what about that angle BCD, children? BCD has to be 90 minus x. So, therefore, shall we compare the angles of triangle ADB with the angles of right triangle ABC, children? Let us start. What is the first point you wish to write? Which are the angles equal to 90? So, angle ADB is 90. It is because of construction. What is angle ABC? It is because of data. Therefore, angle ADB is equal to angle ABC is equal to 90 because of construction and data, children. Okay. Now, which is the second one you want to choose? So, angle A is common to both the triangles. Please observe the figure carefully. Angle BAD is there in right angle triangle ABD, whereas angle A is there in right angle triangle ABC also. Therefore, angle A is common. Come on, what is your conclusion now? Those two right angle triangles became equiangular. Okay, when they are equiangular, we can say that they are similar, which means that they have the same shape. When they are similar, why don't you apply the A criteria, taking the corresponding parts of the similar triangles? So, the first is AB upon AC. What are AB and AC, children? AB is the hypotenuse for right angle triangle ADB, whereas AC is hypotenuse for right angle triangle ABC. So, AB upon AC is equal to AD upon AB. Look at the figure, children. What is that AD? AD is nothing but the angle facing 90 minus x in right angle triangle ADB, whereas in right angle triangle ABC, the side opposite to 90 minus x is the side AB. Therefore, it is equal to AD divided by DB on account of A criteria. You know the next step. So, we need to cross multiply and get this wonderful result. AB square is equal to AC into AD. I think you can recall very clearly, this is nothing but corollary number 1 to AA criterion, children, correct. So, we have calculated what is the area of the square on the side AB, which is equal to hypotenuse AC into that segment AD. So, let us call this as part number 1 in the proof. Okay. Now, let us go to the another triangle, children, that is right angle triangle BDC. Look at the right angle triangle BDC, the angles, and then compare with the angles of the right triangle ABC, children. Come on, start. First, you want to write which are the angles equal to 90. Angle BDC is equal to 90 because of construction, whereas angle ABC is already equal to 90 because of data. Therefore, they are equal on account of construction and data. So, one angle is over. So, angle C, don't you think it is common to both the triangle, children? So, angle C is common to both. So, therefore, you can easily conclude that those two right angle triangles are equiangular. The moment they become equiangular, they became similar. So, right angle triangle BDC is similar to right angle triangle ABC. That means they have the same shape. When they have the same shape, why don't you apply A criterion, children? Take the ratio between the corresponding sides. As usual, first take the ratio between the hypotenuse. BC is the hypotenuse in right triangle BDC, whereas AC is the hypotenuse in right triangle ABC. The BC upon AC is equal to DC upon BC. Look at the side DC, children. In right triangle BDC, it is facing angle x, whereas in right triangle ABC, the side facing angle x is BC. Therefore, it is equal to DC upon BC on account of A criteria. Now, you know that you need to cross multiply this in order to get the square on the side BC. Therefore, BC square is exactly equal to the hypotenuse AC into DC. You know that this one is corollary number 2. Okay, for A criterion only. Okay, so you now know what is AB square, what is BC square, what is Pythagoras theorem is expecting. We want to add both. So, what are the results we got now? So, we have now two things. One is AB square, which is equal to hypotenuse AC into AD. What is the second result we got? We got BC square also. it is also equal to hypotenuse, the same hypotenuse into that segment DC. We wanted AB square plus BC square. Come on, what is that we need to do? We have to just add them. Come on, add. So the left hand side will become AB square plus BC square is equal to the right hand side is AC into AD plus AC into DC. This is our equation now. Okay, focus your attention on the right hand side. How to add AC into DD plus AC into DC, children? It is quite easy. See, AC is the common factor. It is the highest common factor. It is the highest common divisor. Let us divide each term by AC into AD. So, AC into AD, if you divide it by AC only, so what is that we will get? So, AC is getting cancelled. So, AC is getting cancelled. We are left out with AD only. So, open the bracket and say into AD. So, AC into AD. So, write plus below the plus sign only. So, once again divide AC into DC by AC only, you get DC as the quotient. Now, come on, go to the figure and see the segments AD and DC. How are AD and DC, children? If you add them, you get AC. It is all because of rule number 2. There are 5 rules are there given in 2012 textbook. You can understand from that. So, the segments AD and DC add up to AC only. So, right hand side became AC into AC. On multiplication, you got AC square. So, AB square plus BC square is exactly equal to AC square. This is what we wanted to show. This is our Pythagoras theorem. So, we can say hence proved, children. Okay, QED means quad erat demonstrandum. That which is to be proved is proved. Okay, this is, you can remember it as part 3. Anyhow, to prove this theorem, there are 3 parts are there. First, you have to calculate AB square, then BC square, add up. By adding, take AC as the highest common factor, you will get the Pythagoras theorem only. Very easy, children. Please practice this by drawing figures in various fashions with the right angle triangle facing the right, facing the left, facing the bottom like this. So, you have to practice like this with different alphabets also, so that you can remember this theorem for a very long time. Okay, in a right angle triangle, we can construct any similar polygons also on the sides, children. Look at this. Here is a right angle triangle in which this angle is 90. This is the hypotenuse. Here is a regular pentagon. Here are 2 similar regular pentagons are there. So, here also you can understand that area of this regular pentagon is equal to sum of the areas of these 2 regular pentagons also. In other words, don't think that you must always draw squares only like this. You can even draw regular or similar polygons. Even in such case, area of this on the hypotenuse is equal to sum of the areas of the other 2 sides. In fact, you can even draw on the sides of a right angle triangle, taking them as diameters, you can draw 3 semicircles, children. Even then also, you will observe that area of this semicircle is equal to sum of the areas of these 2 semicircles also. Is it clear to you, children? Yes. Now, having understood that the Pythagoras theorem, let us now perform an activity to understand the converse of Pythagoras theorem, children. Here it is. So, here is a triangle in which the sides are 6, 8, 10. Here is another triangle with sides are 7, 10 and 12. Here is a third triangle in which the sides are 2, 4.5 and 7. Imagine the squares on all the 3 sides. Okay, let us calculate their areas. So, area is 100, 64 and 36. In the next figure, it is 144, 149. In the third, it is 49, 20.25 and 4. So, in the first figure, the square on the longest side is equal to sum of the squares on the other 2 sides. In the second and the third, the square on the longest side is not at all equal to the sum of the squares on the other 2 sides. So, in the second figure, the square on the longest side is in fact lesser than the sum of the squares on the other two sides. In the third figure, the square on the longest side is very much greater than the sum of the squares on the other two sides. Therefore, wherever you see that sum of the squares on any two sides is equal to square on the third side, you must conclude that those two sides will contain a right angle. If the square on the longest side is less than the sum of the squares on the other two sides, then definitely those two sides will contain an acute angle, and it is needless to say that if the square on the longest side is greater than the sum of the squares on the other two sides, then those two sides will contain an obtuse angle. With this information, can you state the converse of Pythagoras theorems, children? Okay, can we state like this? If the square on the longest side of a triangle, you take any triangle, see the longest side, calculate the square on that. If it is equal to the sum of the squares on the other two sides, then definitely you can close your eyes and say that those two sides contain a right angle. Or you can put it this way, if the square on the longest side is not at all equal to sum of the squares on the other two sides, then those two sides will never contain a right angle, children. So this is theorem number 2.9 as per our textbook. So this is the figure. So what is the data? In triangle ABC, AC is the longest side, therefore AC square is equal to sum of the squares on the other two sides. So what is to be proved? We have to show that AB and BC, between them there is a right angle. So we have to prove that angle ABC is equal to 90 degrees. So let us compare Pythagoras theorem and converse of Pythagoras theorem like this. So here are the figures for you. Data in triangle ABC, angle ABC is 90. To prove AB square plus BC square is equal to CA square. So in converse of Pythagoras theorem, we just say a triangle, an ordinary triangle ABC, in which the square on the longest side is equal to sum of the squares on the other two sides. So in such a case, you have to show that angle ABC is 90. So observe that data of Pythagoras theorem has become to prove, and to prove of the Pythagoras theorem has become data. If you interchange like this, then the new theorem you obtain is called converse of Pythagoras theorem. In the figure, in the Pythagoras theorem, we write 90 degrees in the at B, but whereas in converse, since we have to show it as 90 degree, we should never mark it as 90 degrees. Having understood Pythagoras theorem and its converse, we shall now explore another important theorem, children. So here is a right angle triangle ABC, in which angle ABC is 90 degrees. So BD is perpendicular to AC. So for brevity, select the length AB, which is opposite to angle C, call it as C units with a lower case. So the length of BC opposite to angle A as A units, and the length of AC, which is opposite to angle A, call it as B units, and finally the perpendicular BD as P units. So with this we have to show that 1 by P square means 1 by BD square is equal to 1 by A square means 1 by BC square plus 1 by C square, that is 1 over AB square. So 1 over P square is equal to 1 over A square plus 1 over E square. What a beautiful result, children. This is called reciprocal Pythagoras theorem. The proof is very simple, children. Come on, with the help of area, we can show that area of triangle ABC is half into A into C, which is also equal to, if you make hypotenuse AC as the base, it is half BP. So cancel half of on either side. AC is equal to BP. So we wanted 1 over P square. So first we will calculate P, and then 1 over P, and then 1 over P square. So for B square, if you substitute with the help of Pythagoras theorem as A square plus C square, we get this. Now can you split it and write it like this? A square by A square C square plus C square by A square C square is equal to 1 over P square. So we can cancel A square on in the numerator and denominator to get 1 over C square. Similarly, C square is getting cancelled. We got 1 over A square. Okay, so that is equal to 1 over P square. So simple, children. In fact, there are many other ways, alternate ways are there proving this. So please try to explore them. So we have understood that in a right angle triangle, if you draw a perpendicular, the length of that reciprocal of the square of that is equal to 1 over A square plus B square, whereas we have already proved BD square as AD into DC, children. Can you remember, can you recall this? This was the third corollary to A criterion. Now we know 1 over P square as well as A square also. Here is a beautiful parallelogram in which all the sides are equal, definitely it has to be a rhombus, children. And you know diagonals bisect each other, therefore AO is equal to OC and BO is equal to OD. So we have to show that AC square plus BD square is equal to 4AB square. You know that in a rhombus the diagonals bisect each other at right angles. So there are 4 right angle triangles are there. Take any one of them and apply the Pythagoras theorem like this. So AO square plus OB square is equal to AB square on account of Pythagoras theorem. AO square is nothing but half of AC. So AC by 2 the whole square plus BD by 2 the whole square is equal to AB square. Expand using laws of indices, take LCM, cross multiply, you get the result whatever you want. So AC square plus BD square is equal to 4AB square. The same thing, children, can be stated in the form of a statement. In a rhombus, the sum of the squares and the diagonals is equal to 4 times the square on any one of its sides, or you can expand it and say that 4AB square is nothing but AB square plus BC square plus CD square plus DA square. So let me tell you how to draw a rhombus by just using a scale only, children. So first draw the AC. In fact, this is nothing but our diagonal, one of the diagonal. Mark the midpoint as O, that is AO is equal to OC. At O you draw a perpendicular like this, call it as BD. So BO is equal to OD, but you should never be equal to AO and OC. So take scale and pencil, join all the 3 vertices, you got a beautiful rhombus, children. See, with the help of a scale only, you can draw so nicely a rhombus. So let me take up 2.5 exercise 6 problem. Here is an equilateral triangle. So if you draw a perpendicular, you know it is divided in 2 equal parts. Take one of them, apply Pythagoras theorem, then simplify, you get, so a root 3 by 2 is equal to height. So therefore, in an equilateral triangle, the height is always given by a root 3 by 2, where a is the length of a side of an equilateral triangle. So this is very, very important, children. While you are discussing trigonometry, this will help you a lot. So please remember, this we obtained with the help of Pythagoras theorem only. So in this last session, 8th session, we learned the proof for Pythagoras theorem and learned something about converse, 2 worked examples also. Can you take down the homework? 5 worked out examples and 17 problems from exercise 2.5. So far in this chapter number 2 triangles, see, children, we have understood about 9 theorem. We hope that you have enjoyed each and every bit of it, that is all the 8 session of this chapter. Dear children, do you remember that we started with the chapter number 2 triangles with the 5 challenging situations or questions from various chapters of our textbook? Is it possible to recall and answer them, children? Can you remember the volume of a frustum? So this can be easily understood now with all the concepts we have discussed: mirror formula, concept of trigonometric ratio, and even the golden ratio, golden rectangle, gauge also. So all these things can be understood with the help of our concepts we have discussed, children. So with this, we thank you very much, and with all our wishes, thank you, children, once again. So I am T.K. Prasannamurthy, retired headmaster, Vijay High School, Jayanagar, Bangalore, children. Namaste, children. Namaste. All the best, children. Thank you very much. Namaste.
Anudina